Welcome to Lecture 3 of MCS 481 on computational geometry. So the topic of today is line segment intersection. So line segments are very important. In our first lecture, I stood up to explicitly emphasize what I meant by a line segment. A line segment is the most non-trivial example of a convex set, all convex combinations between 2 points. The purpose of this lecture is to introduce gradually, step by step, how you would develop an algorithm to intersect line segments. In the first lecture, I said that most of the algorithms are n log n, and I lied. So it will turn out that some inputs will lead to quadratic time algorithms, no matter what. We will also introduce the plane sweep algorithm. Voronoi diagrams were mentioned in the first lecture. The notion of line sweep algorithm, actually in general a plane sweep algorithm, will occur in several spots in this course. We will introduce that. This lecture is in preparation to the next lecture where we will see the algorithm proper. The purpose of this lecture is to define step by step the cases and also the data structures that will be used in the algorithm to solve the line intersection problem. Okay, so why do we want to do this again? The location of the nearest coffee shop was one of the problems. But often where we have to overlay the locations of the nearest coffee shops with the maps. Most geometrical information is stored in layers. And if you start to combine one layer with another, then you will need to intersect. We will make a mathematical abstraction of this. In this course, we are mainly interested in the mathematical ideas as well, or mostly interested in the mathematical ideas. And this lecture is mainly oriented towards paper and pencil exercises. So we will focus actually not on the complete map overlay problem, although then lecture 5 is on subdivision overlay. We will get close to that. Today we focus on intersecting line segments. Okay, here is the problem. So we have a set of line segments, set S, finite set. N is, as always, the dimension. We start counting from 1, why not? And every line segment is a tuple of tuples. So we have the x and the y coordinates in the first tuple, so that defines the first point. And then we have the x and the y coordinates of the second point. Here I have it with the convention. So let's look at the example, at the drawing. There is not a convention that the first point should be lowest, but it is here so drawn in the example. So the input consists of a set of tuples of tuples. The numbers for the coordinates are by default in this course integer points. So what is then the output? The output defines the intersection points. So also a tuple of tuples, and it's not necessarily the order. So it's also a set. So the first tuple in the tuple of tuples indicates which points that we intersected, so which line segments that we intersected. So the I and the J is from the ith segment and the jth segment. And the second tuple in the output, in the tuple of tuples, are the coordinates. Again, they can be, if we are giving input data that is exact, they can be nice rational numbers. Can also be floating point numbers. But for today, let's focus on very simple inputs. All right, talking about easy inputs. Here is one example. So we have all our first points lined up to the left, all the endpoints at the right lined up. All the endpoints are lined up at the right. And you can start computing all the intersection points here. So I can start counting. So everything that is inside this here. So let's start counting them. But actually the easy input was also intended to be easy. So every line segment intersects every other line segment. So you can compute just by multiplying the number of combinations, how many line segments you have. So if every line segment intersects every other line segment, let's focus on A6, B6. So then we have 1, 2, and I'm actually now already wrong, 1, 2, 3, 4, 5. So we have 6 lines, and every line intersects each other line. Then we have 30 intersection points. So well, that was easy. Can even be easier. So here you see I should actually have started with this example. This is really easy. Number of intersection points, 0. So for 6 lines, it can be either 30 or it can be 0. And that leads us to the notion of intersection points. And you see that I actually did this already wrong. It's not 30, but it is 15. So the number of I counted points double. So here, this is the true upper bound. All right. In the design of algorithms, complexity is actually important. We can actually say something about so the cost is something that is a property of an algorithm. Complexity is something that is a property of a problem. So no matter what algorithm that you are using, just building the output will require n times n minus 1 over 2 steps. So that is a lower bound. I will give the formal definitions in a minute. So we are interested in asymptotics. So the 1/2 is a constant, doesn't really count. And if you expand this, n square minus n, the minus n actually also doesn't matter. So this is an n square. Complexity is important. So also you could say that this is the worst case of any algorithm, but it's a property of a problem as well. So if you distinguish worst case scenarios, then this is a worst case. In general, we say that an algorithm is output sensitive if the running time is proportionally to the size of the output. When you would consider the convex hull in any dimension, then you can have an exponential number of faces of a certain type. So even though the input dimension, so on input, so the input is actually the given n. So we have n line segments on input, but the output can be n square. So this is an important notion. And it's important to realize this before we start designing our algorithms. So there are the really simple cases, no intersection at all, and then there are the cases where we have many, many intersection points. Okay, so to be complete, so this course follows an algorithms course, but you can take this course without having the prerequisites algorithms course. So we have been using the big O notation, and the big O is actually the most important definition here. So we are working with asymptotics, so we look for the long run. So as n goes to infinity, it's not infinity, but it can be made arbitrarily large, and it's larger than any threshold. So the n naught here is the number at which the startup cost of your algorithm would actually dominate. So there is some fixed startup cost, and your dimension should be way past of that. There is the omega, and there is the theta. So the omega gives a lower bound, so the big O gives an upper bound. So that's why the big O is actually most important. You get to capture everything. The big omega that was used on the previous slide is to indicate that there is asymptotically a lower bound. So any algorithm can't really do better, or it is the worst case scenario. Then there is big theta. Big theta is when you have an asymptotic sharp bound. And this is also important in actual applications. You have a completely predictable running time. So the order is quite predictable. Sometimes it's not good if you have inputs that can be done in constant time and then other inputs that take quadratic time. So as far as expectations go, you may like to have a big theta. But as in the line intersection problem, that is actually not achievable. Okay, plane sweep algorithms, or here in particular line sweep algorithms. So how will we decide that we are in the easiest case of no intersection? Well, if there is a separating line, if there is a line that separates the line segments. So this L here, it's just a number. So L is a number, it's a value of a y coordinate. So this slide contains a definition. Y coordinates do not overlap. So what this means is that the L, this L here, all the y coordinates of segments Si, so in particular A sub I, B sub I, they lie above, and the other ones lie below. Or you have it the other way around. So you have two line segments, their y coordinates do not overlap if all the y coordinates lie at the same side as at opposite sides of the line. So in some sense, this is also a mathematics course. I try to be brief on the slides, and there is one sentence here that introduces the idea of how do you decide whether you are in the case when you have no intersections. As a formal mathematician, it's important to actually write it down formally. So given two line segments, what do you mean by the y coordinates do not overlap? So that will be the first exercise. Okay, but actually what I wanted to introduce is the algorithm, is the sweep line. And it's an imaginary line. So in the algorithm, it will just be a number, but it's an important number. It's here this fancy L. I emphasize this with the horizontal line. There is a pre-processing. Sorting can be done in n log n. So in some sense, if you like, it's a modification of the input. So the input was a set of line segments. You can immediately replace this by a sorted list where every point is sorted by the y coordinate. For the Python programmers among this, look into the specification of the sort method. There is a way to handle this, but let's not digress here. So we have a line, a fancy L, but it's actually also what is called a sweep line. So we have our segments ordered now, and we will start processing then by imagining. The imagined line will actually start from the top, start above the highest y coordinate, and gradually moving down. So I should also say that we actually sorted from high to low. So the initialization is that we start above all line segments. We slide down gradually and then we encounter events. Notice that we started the first lecture with making combinations of line segments. We passed that stage. We don't want to have any more experiences with algorithms that run into the power tree. And I should actually also have said this. So if you are a pessimist and always expecting the worst case, then actually making all combinations is fine. So if this is the worst case scenario, making all, if that is your application, you expect always that many intersections, well, that's fine. Okay, we will not have this because our maps, they can have millions of line segments. So, and actually we do not want the worst case. You do not want to, you will be never in. So, and line segments are not lines, so they are short. So the worst case is actually quite a very specific case. Okay, we will distinguish two types of events for now. So we have the highest endpoint and we meet the lowest endpoints. So I talked about millions of line segments. The sweep line is actually, if you like, a way to narrow down your, to focus on a particular set of line segments that can have intersections. It is a loop, and as algorithm developers, when we think about the loop, we think about initializations, what happens at the end of the loop, but there is also the loop invariant. So all the intersections with line segments that are above the sweep line have already been computed. So there will be events. So if we have an endpoint of a segment, the event is that that segment is no longer in what we will call the status of our algorithm. But this is the idea. The key idea is that we have a number, the height, fancy L, and we imagine a sweep line. Okay, so I mentioned the status. Here it is. And the first exercise is meant to pause a little bit and to think about the status. So what is the status? Why do you need it? Well, it is the subset of the input that is currently under consideration. So it's the subset of the segments for which there may be an intersection. So here you see the formal definition. So of the set, big S, all the segments for which the intersection is not empty. So it seems like we're doing another intersection problem, but we are intersecting with a line. So deciding again whether, if you think algorithmically, you have a big set S and deciding again whether you intersect the status, the sweep line. Well, it's checking whether the fancy L here, which is essentially the height, whether that lies between the y coordinates of your segments. So here uh, so this is a geometry course. You actually see that for every line segment, we have one point that is above the sweep line and one point that is below the sweep line. Okay, what is the status in case when the y coordinates of the line segments do not overlap? What is it? The purpose of this exercise that now you fill in the definition of y coordinates. So the exercises can be answered by sentences. So what does it mean that y coordinates do not overlap? So I paused a little bit on this, so now we should backtrack to the previous slides. I gave the definition with a picture. Y coordinates of two line segments do not overlap. What does it mean? And what is the case? So, I mean, the answer is actually the answer to the exercise. There is no overlapping. Then actually the status of non-overlapping. So there's one very plain answer, but I will not give it now. But the purpose of this first exercise is that one, let the definitions sink in. So the status is extremely important. I gave a formal definition. But now actually we see that we also needed to know what was the formal definition of segments for which the y coordinates do not overlap. What does it mean in that case? So starting this exercise is writing down in words, your own words, what does it mean? All right, events. So we have the red points. So we have, and actually this is before and after. So here you see the green points are the intersection points that are computed at the event. So when the line is touching, so when the line is above where it currently is, then there are no intersection points because the first two segments that were encountered by the sweep line, they do not intersect. So no events, so no intersections there. But there is a third segment comes in, and in the status we now compute, and again this is a primitive operation. So I should also refer back now to vector calculus. Vector calculus solves this problem. So, and this could have been another exercise. So think about that could have been exercise 0. Go back to your vector calculus courses and check how to get the coordinates out there. And I mentioned in the very beginning integer and rational arithmetic. It's fine to do this with floating point numbers. All the intersections in this case are not degenerate. We will deal with degenerate cases later. All right, so here you can see the evolution of the algorithm. So it looks complicated. So it looks like it's not a bowl of spaghettis, but it's a heap of needles. But you can go through this heap of needles very systematically. So you see at the next event, there is the next segment that comes in. So we have 4 segments to consider. We have all the 4 intersection points computed. And then at the next stage in the algorithm, I have it here that all the lowest points are the same. So then actually all the 4 lines leave the status. All the 4 line segments leave the status. Okay, I'm halfway in this pre-recording. Now actually we have the geometric algorithm. If you had to solve this problem by hand systematically, you should be able to actually do this. So let us reflect a little bit on this. So in words, we have actually the algorithm in one sentence. So for every new segment that enters the status, we test whether that um, new line segment intersects the status. All right, here is a input. So I have 8 line segments in a specific constellation. You can immediately see what the 4 intersection points are. If you think 8 is too much, you can truncate, and if you like, you can start with the first 2. But for the answer to this exercise, I want actually 8 sentences because there are 8 events initially, and you can make drawings as well as you do this, but and you can also submit drawings by all means if you solve this homework exercise. But what you do is you run the sweep algorithm, and as the you have the 8 numbers, the 8 endpoints that are lined up very neatly. So this is a nice case, you know what the output is as well. The question is relate the number of intersection tests to the number of intersection points. And that is probably requires some reflection here. So we have 4 intersection points, but we actually do a lot of work. So if the last segment comes in, we actually have to, so again, this is deceptive. If you do this as a human, we have great pattern recognition abilities. So we will immediately see that, hey, we only need to check with 7. But your computer will only see the height and will actually not know the slopes using a vector calculus term again. So your algorithm needs to do 7 intersection tests. So there is the worst case scenario for the running time, but there is also the expected number of, so the actual number of line intersection tests that this needs to be done. And that is related to the size of the status. So that is actually the answer. So the status, it was a formal definition. It is a very important notion, second to the line sweep. So the answer to the second exercise is that the size of the status determines the amount of work that you have to do. In the worst case, the size of the status is your entire collection. And actually, it didn't look that way, but actually it looks like this is also not a good case for our algorithm, for our sweep line algorithm. Okay, adjacent lines. So this is indicating an improvement here. So the reflection, so I tell actually the answers to the exercises, which goes too fast. But the purpose is of that actually the second exercise was also a motivation for improving the algorithm. It makes sense to consider which lines are adjacent to each other. So, and you should only intersect adjacent intersection lines. So that's the main thing here. So the top line, if we want to be clever, and who doesn't want to be clever, we will intersect only line segments that are adjacent to each other. And here you can see how we can encode the status. So the status, when I defined this as a set, we can actually improve this. So we should actually, as soon as we add a new line segment to the status, we should insert it and take care of its adjacency. So the order can be done physically, but it can also be represented by a sequence. So we have the labels for the sequence 1, 2, 3. So you see when the sweep line descends, the adjacency changes. So that's actually the other thing, what I'm telling you now. It's not only important to monitor, to insert a line segment into a sorted status, but we also actually now have a third type of event. First type of event, a line segment entered. Second type, a line segment leaves. Now the third type of an event, we have a change of adjacency. And this may happen after the computation of an intersection. So actually we have the intersection points themselves that become event points. So all the points of the line segments were events. Now actually we have also the intersection points. And thinking ahead on the cost of the algorithm, so now you can see that the running cost of the algorithms becomes again output sensitive. So we had the input dimension, the number of line segments, but actually now also the intersection points, which belong to the output, they are event points. Something needs to be done at those points. All right. Okay. Problem now. We are making things more efficiently. We are doing less work. Very advantageous, but do we do sufficient work? Okay. If the adjacencies are changed, will all intersections be detected? Is this important? Yes, it is important. Here is a lemma. So if we have two line segments that are not horizontal and they intersect in a point, if there is an event point above the line, actually then there is an event point above the line where there are adjacent. There is the lemma and there's the picture that goes with this. So the picture often makes this look like trivial. So if you change adjacency, well, if two segments are still adjacent and you start intersecting them, yes, but does that suffice? Of course it does if you make a picture, but if you read the lemma, it's formally written down to non-horizontal line segments, so they do intersect, then actually you will detect them by an event point. And the two event points here for the picture are actually the event points that are the top points. Okay, a lemma needs to be proven. So here is the proof based on the observation. So the picture is gone. So it's important to keep the picture in mind. So in some sense, slides are not very good. So we should make drawings. Um, okay, what are the observations that we meet? So we have two line segments, so they intersect. Will we find that intersect point? Well, there should be an event point so that they are adjacent. So if the line is just above the point of intersection, then the two must be adjacent, and then they will be covered. So if you are analytically minded, then this is a perturbation argument. So you could imagine the line sweep passing through the intersection points. You are at that event. But the point is, you actually don't really know that intersection point yet because you might have missed it. So you can't really say that you are at that. Well, suppose that you're just above it, just an infinitesimal point. Well, if that happens, then they must be adjacent. And adjacent once we intersect enough. Okay, and now the second point looks kind of strange. Well, at some point, the status was empty, so for high enough coordinates. So there must have been an event point where the two ones that have an intersection points became adjacent. So the proof is actually, I wrote it here in 2 bullet points, 2 observations. So the main key is actually the first observation. Whenever two lines intersect, there must be a point where they have become adjacency. So they have been tested already. All right, let's be a little bit more careful now and start itemizing things. So we have three types of event points. The upper end, um, so we have to look for, so now we have to encode also the adjacency. So we have to look for the neighbors of the line segment. How this is done, primitives, and the intersection points are added as events. At every intersection point, it's a new event point, so you have to find, you have to update the adjacency. So there are two line segments that are in play. Again, it's a primitive because it concerns a constant number. So the new neighbors, actually, you may have to consider everybody in the status, but I'm sorry. So it may still, every operation may still depend on the size of the status. So the intersection points are event points. If you are at the lower end, uh, because of the adjacency, you have actually more work to do. So the lower end appeared to be um, the trivial case that you just have to delete something out of a set or out of a data structure. Now actually what you do is that you may have new intersection points because you only test the intersection for segments that are adjacent. So you have to update the adjacency information and test for intersection. Okay, at this point, it turns out to be very complicated. So you may want to think about, hey, wait, the worst case was intersecting all cases. I'm not going to do all that. Well, let's get to the data structures. But the point of this exercise here, and I will go a little bit faster now, is that actually you have 7 line segments. So you have 7 events already. but that for every event point, you will actually write down the adjacency information. So you will actually write down the sequence of points. So how the line segments are ordered. It starts with, I think, 7 might come first. So 7 comes first and then 1 comes in. So 7 and 1, they are adjacent. Then 2 comes in. You have to verify that the order will be then 1 to 7. So 2 is adjacent to 1 and is also adjacent to 7. So you have to check. So for every event, you have to run through this. So it may be a little bit tedious, but it will increase your appreciation for the data structures that are following now. So whenever there is something complicated to keep track of, you need data structures. And this course actually follows data structures. So this is a course in the computational track. Not everybody may have taken data structures, but the course is recommended, is required for algorithms. We will be using a queue stored as a balanced binary tree. So it's also called a priority queue in the proper knowledge. So there is a order between event points. So we define this order. So 2 event points. So Q and P, we actually are comparing their heights. Or if they are the same, then actually we are referring to the x points. So here the less than, so actually it's a less than, it actually means that the priority of P is higher than the priority of Q. Either because the height of P is higher than Q, or we have the same height and then there are the x coordinates. Okay, so here now you see the balanced binary tree. The bottom line here is that updating, and in some sense I should say that the data structures course may uh, brand some chill around some people. In our case, we will use results of data structures. That's also the point of using the software library Seagull. Seagull actually provides us with these operations, and so don't worry about this. But if you really want to know the details how this is done, then this is done with data structures. So here you see the representation of the event queue. So we have the picture, our line segments, and this imaginary sweep line. And then you can see how the adjacencies are encoded. So the Kate segment is adjacent between I and J. So I came actually in earlier. So that's why it is. So you can see the heights, the 2 children. I'm probably a little bit running ahead of myself here. So there is a particular way to encode this. So the L is adjacent and also the I is adjacent. And then for L, we have also the adjacent points. Okay, I'm running also a little bit out of steam. Of this course, and with this slide I make the transition to the next lecture. So in the next lecture we will do this way more formally, but this is the global algorithm. So the algorithm as we have introduced it step by step. So we have an event queue and we have a status as our two data structures. And then we will process the queue of event points. Initially, and then there is the subroutine, the handle event points, what the update does of the adjacency information, and then the computation of the new intersection points. Okay, in scrolling back, so I don't like to scroll back, but so the event queue is different from the status. So that is important realization. I did not emphasize this well. So there is a distinction between the two. Okay, I'm 45 minutes in and I do not want to run over time. So the purpose of this lecture was that you could start reading the textbook and you get some more familiarity with a very important but very complex task, or which could look into lead something that's quite bad. I do not have any demonstration ready, so I would also need to qualify and press and clarify what I actually meant, but if not already done so. In some sense, there might be, this is the third lecture at the end of the first week. There may be some urgency here already. I feel that working with a computer is a excellent way of getting a completely different way to look at things. So it's strongly recommended. On the other hand, I allow that this course is taken as a theoretical computer scientist. But then one of the social assignments would be that you try to team up with a partner. Um, so the exercises are recommended. The exercises that are on the slides are for me mainly meant to pause, to indicate that, hey, in order to continue, you must actually do this exercise or in your head. So I will not be able to collect everything, but it's still very important. The exercises, so these are exercises 1, 2, 3 of chapter 2 in the textbook. Okay, so this is the first lecture on chapter 2. We will formalize the algorithm for line segment intersection in the next lecture. And then there is the subdivision intersection that we will treat in the third lecture.